Hello, everybody. The title of this presentation is Closed-form solution for the state localization problem in a softening bar under tension with the continuum damage and the embedded discontinuity models. My name is Gelacio Juárez-Luna, and my co-workers are Ángel, Uriel, Martínez-Miranda, and Gustavo, Ayala. The outline of this presentation is the following. There is an introduction, the objective, a variational formulation, the boundary value problem, the closed form solution, and some validation examples. The problem is the following. Consider this bar fixed at the left end and loaded at the right end, loaded until a crack occurs. Well, this crack is modeled with a continuum damage model. In this model, the effect of this crack is smeared along the length of the bar. In the embedded discontinuity model, this crack is modeled as a displacement jump at the localization zone. Bazan and Planas and Jirasek and Planas provide an expression to compute this ultimate displacement as the multiplying this strain by the length of the bar. But there is no solution to compute this low displacement curve or to compute the displacement along the length of the bar or the strain or the stresses. Then the objective of this work is the development of the boundary value problems and closed form solution for the state localization in a softening bar with the continuum damage and the embedded discontinuity formulation. Let's see the kinematics to represent this crack in the embedded discontinuity model. The displacement is approximated with a linear function, so the strain has a constant value as it is the derivative of this displacement. In the embedded discontinuity model, the displacement is this, which corresponds to this regular displacement and this jump. This jump models the crack. And the derivative is the strain. And here we have regular strains outside of the localization zone and unbounded strain at the localization zone. This is the kinematics. The constitutive model for the continuum damage model is given by these stress strain curves with linear or with exponential softening. For the embedded discontinuity model, the constitutive model is given by these stress displacement jump relationships, also with linear or with exponential softening. The variational formulation for this problem, for the continuum damage model, is given by this, by the following functional. This term corresponds to the strain energy at the volume of this bar, and the external work given by the body force and by this external work is given by these two terms. For this bar with the embedded discontinuity model, here we have the strain energy outside of the localization zone, the external work by the body force and by the load, and also this energy at the localization zone. With this functional and with this Euler-Lagrange equation, For the case of the continuum damage model, substituting the previous functional in this Euler-Lagrange equation, it is obtaining this equilibrium equation, but with a nonlinear stress-strain relationship. For the embedded discontinuity model in this bar, it has two independent variables, the regular displacement and the displacement jump. So we have two Euler-Lagrange equation, and substituting the previous functional, it is obtaining the following equilibrium equation, and this relationship which has to be satisfied by the constitutive model. Then, solving this equation, we have, in this case, this equilibrium equation for the continuum damage model, but with a nonlinear stress-strain relationship. Integrating twice this equation and solving for the displacement, it is obtaining this displacement. The derivative of this corresponds to the strain, and here we have the stress multiplying this equation by the elasticity model and by this moduli. Then the closed form solution for this bar, but with the embedded discontinuity model, is obtained by solving this equation, integrating twice, and here we have this regular displacement, solving from the constitutive relationship, it is obtaining this displacement jump. With these two, it is obtaining the displacement along the length of the bar. The derivative corresponds to the strain, and multiplying the regular strain by the elasticity modulus, it is obtaining the stress. These two solutions are for linear softening. Let's see this closed form solution, but also for exponential softening. Here we have the displacement, the stress, and the strain. This is for the continuum in this bar, but with the continuum damage model, and for this the same bar but with the embedded discontinuity model. Here we have the displacement and strain stress for the linear and exponential softening. These solutions are reported in this paper by Gelacio, Ángel, Uriel, and Gustavo, Ayala. Here you can find all the mathematical treatment. Let's see some examples. This first example is this bar, which is 60 centimeters length, and it has a diameter of 30 centimeters. Here you can see the mechanical properties. The solution of this bar with a continuum damage model, here you can see the displacement, the strain, and the stresses. The solution of this bar with the continuum damage model, here you can see the displacement, the strain, and the stress is the same. The results for both models, the low displacement curve is given here, where for linear softening, we obtain the same results for both models. And for the exponential softening, we have different curves for the continuum damage and for the embedded discontinuity model, but the area under both curves is the same. Now let's see the displacement, but along the length of the bar when the low P is the peak load here. So we have the displacement along the length of the bar, the strain, and the stress for both models. Then when the peak load is, when the load is half of the peak load, here we can see the displacement along the length of the bar with the continuum damage model and with embedded discontinuity model. There is a jump at the localization sum which simulates the crack. The strains are relaxed at this part of the bar with the embedded discontinuity model, and the strain is unbounded at the localization sum, and the stress are the same. When the low P is 0 at this point, the crack is completely open, and it is simulated by this displacement jump with the embedded discontinuity model. And here we have a linear function for the continuum damage model, the strains for the continuum model, and for the embedded discontinuity model, the strain is relaxed at this part and unbounded at the localization zone and the stress. Let's see another specimen, but with snack bar behavior. This is a bar of 45 centimeters length with a diameter of 11.3 centimeters. Here you can see the mechanical properties and the results. For the continuum and for the embedded discontinuity model, the low displacement at this right end, for the linear softening, both solutions are the same, but considering exponential softening, we have different curves, but the area under these curves are the same. But the embedded discontinuity model show this snap back behavior at this part. Let's see the stress strain curve for the continuum damage model and the stress strain curve for the embedded discontinuity model here, because the strain are relaxed in this part. As conclusions, closed form solution for the cell localization problem in a softening bar were developed. Closed form solution for the displacement, strain, and stress. The difference between the continuum damage model and the embedded discontinuity model are related with the kinematics. The continuum damage model simulates the crack but along the length of the bar, whereas the embedded discontinuity model simulates the crack as a jump displacement and the localization zone. In the classical continuum damage model, the fracture energy required to open a crack is smeared into the entire domain, whereas in the embedded discontinuity model, this fracture energy is released at the localization zone. The dissipated energy under the global load displacement response of both models is the same, which is in agreement with the dissipated energy during the development of a crack. However, the kinematics of the embedded discontinuity model simulates adequately the kinematics of the strain localization problem in a softening bar. That's it. Thank you so much.